as we have seen PSRO, the relaxation techniques. So what we have here, so this is a relaxation parameter. So this relaxation parameter varies 0 to 2, is it? So this with respect of the relaxation parameter, our iteration, number of iteration, time taken is vary with respect to algorithms we have seen in elliptic equations. So for example, in this over relaxation parameter, when 0 to 1 is under relaxation. Okay. When beyond the 1, it's a over relaxation. Okay, these things are you have to note. When during iteration process, whether you have to put a over relaxation or under relaxation with respect to your problem. So always, so many problem obeys under relaxation. Okay, so all the relaxation value you have to give a 0.22 within a 1. It will give us a easier and come faster. Yeah, our solution result is come faster than over relaxation. So under relaxation limit is with respect to our problem vary, as well as when you give this under relaxation, there is a coupling between time, iteration and technique. So we will see this technique in now graphical representation. For example, if you look at the chart, so this is a comparison between elliptic algorithms. So what are the elliptic algorithm available? What are the available algorithm? I have scaled in x direction. Okay, so PSOR and PGS. PGS means point Gauss Seidel. LGS means line Gauss Seidel. LSOR, line successive over relaxation. Okay, PSOR, point successive over relaxation. Okay, so corresponding iterations available in a y direction. Okay, and time consumed by the algorithm in the head of the bar. For example, if you look at the PGS point Gauss Seidel, it around approaching a 600 iteration within a 5 seconds to give our solution. Okay, I think this is a maximum. This is the maximum iteration. Okay, so to solve our problems, the iteration is vary with respect to algorithms. Okay, so if you look at the PSRO and LSRO, it's a very gives a small number of iterations. Okay, for example, LSRO it consumes minimum time 1.4 seconds. It's below 100 iteration. LSRO and PSRO. So when comparing a line PSRO and LSRO again, LSRO is a very less iteration. So it gives a quick results. So this is an important study you have to observe in this plot. And so origin is successive over relaxation origin is came from point Gauss Seidel. So the point Gauss Seidel consumes more time, more iteration. Okay. Even it's a more iteration, it consumes only 5 seconds compared with the line Gauss Seidel. Why? Because of line Gauss Seidel operates and manipulations higher compared than PGS. Okay, even higher iteration, it consumes 5 seconds, but LGS consumes 7 seconds. Because of it produces a large number of matrix. So it's require more manipulation, so more time consumption. So that's why it's a higher, even it's a small number of iteration. Okay, and I said that when you change the relaxation values, okay, when you change the relaxation values, definitely the coupling between time, iteration and technique is there. For example, the relaxation parameter in the LSO technique. Okay, again the vertical axis shows iteration, horizontal axis shows relaxation factor. Okay, so in the relaxation factor, so I have given it's a over relaxation 1, 1.1, 1.2 up to 1.4. Okay, so in this relaxation factor vary, definitely our iteration also vary. Okay. So when you up to some limit in the center of the plot 1.27 relaxation factor. That is when you increase the relaxation factor up to 1.27, definitely what happened? Our iteration is reduced. Okay, again when you beyond the limit of 1.27, it's again increased. So it's not for a constraint and constant graph, it's vary with respect to our technique as well as our problems. So we have plotted these values for only the square plane we have solved in a fluid. Okay, and manually you have solved. So the value when you calculate the problem calculated by using LSOR, it is vary with respect to our relaxation technique. So this is the noted thing here. Okay, and this is for LSOR technique as well as RD scheme. Okay, alternate direction implicit. So it's also when you vary your relaxation factor, it's gradually decreasing up to certain limit of 1.27 again relaxation factor. When you change the value beyond the limit of 1.27 again it increases. Okay, these things are you have to note. So iteration is function of relaxation factor. This is a general thing in the plot. And like that, when you use a PSR technique, so it's a stable. Okay, in the up to 1.98. Again, you can see the curvature. Okay, like C section, upwards, concave section. So again, up to 1.78, it has reduced our iteration. When you increase 1.78 above the relaxation factor, we will again, it has increased the iteration to converge our result for PSR technique. And this is graph for time consumption with respect to our iteration. So some of technique it consumes some more time, some of technique it consumes less time to reach a certain iteration. That's a plot show. For example, the PSR method consumes up to 1 second, just 52 iterations. Okay, 52 iterations consumes 1 second, and 574 iteration required to reach a 60 second. Understand? So like that it's with respect to our plots, okay, with respect to our techniques. And like LSR also, when the iteration vary definitely, our time also vary. So here noted things are, which one is a minimum iteration? 36. Okay, 36 at least it consumes 1.5 or 1.2 seconds. And 308 iteration, it reaches 5.5 seconds. And like that, alternate direction implicit scheme also, it's a good. Okay, so here, all the techniques within the 10 seconds. Okay, all the algorithm works within the 10 seconds, it gives a solution. But when you solve it manually, it consumes more time. Okay. So how the elliptic algorithm work and vary. So with respect to so elliptic algorithm is a strong coupling between time and iteration as well as relaxation factor. So with respect to these three parameters, definitely we will get to whether our solution is faster or delayed. Okay. And the error generation we have to fix. For example, the residuals and convergence is a function of errors. So how can I fix our error? So generally, before you start your calculation, as a user, you have to fix your what's allowable error. Okay, in our problem. For example, I have fixed only 0.1 instead of 0.1, 0.2. Up to 0.4 is allowable. Error may present. It's allowable. Beyond the limit, definitely our problem doesn't coincide with our exact solution. So that's why you have to fix your error allowable is within a 0.5 itself. For example, I have fixed a 0.1, it's a error max. Okay. So how can I calculate for present problem in our error? So error generally like a G. Can you remember a G? Amplification factor. So it's a modulus of temperature, right? N plus 1 level temperature at 10th level, modulus. And it's for total sum of how many nodes you have. For I equal to 1, 2 to calculate our problems. Okay, so how much error present in your problem you can calculate by using this formula. And before that you have to fix your what would you allow maximum error. Okay, so this two interconnection is definitely the error definitely when getting an error it should be less than the error max. Error is beyond the limit, suddenly the graph shows your convergence is not converged or it's again increasing towards the unstable solution. So you have to remember these two steps when you doing iteration of your problem. Okay. So your convergence and stable is purely function of this error growth. So you have to minimize this error by using a del x del t values. And this is a general procedure to calculate how the error propagation takes place in your problem. Okay. Now, entering to our another type of problem in CFD. So up to this section, what we have finished, how to solve elliptic type of problems, parabolic type of problems. Now remaining is hyperbola. So there is also, again there is a space marching, time marching we have applied here, and general categories are hyperbola problem is again I can split up into a two level, so explicit and implicit. Okay. So in the explicit form we have again Euler FTCS scheme in a hyperbola problem. Again Euler FTFS scheme and Lekt's method, again leapfrog and midpoint leapfrog method. Midpoint leapfrog and interesting thing is in the hyperbola is upwind difference. Okay, these are the explicit approach available techniques to solve our hyperbola problem. Going to implicit, the same thing, always Crank-Nicolson and Euler implicit, then one more technique available, Crank-Nicolson, Euler. First step upwind differences. Okay, so this is also available. So now in this lecture we will see each of techniques, and finally we will get how to solve the non-linear equations. Because if you look at the one-dimensional wave equation, is this linear or non-linear? One dimensional wave equation is dou u by dou t minus a dou u by dou x. Is this linear equation? Because of a and u not coupled. Okay. So a is constant here. So many of problem now in this case deals only linear type of problem solving. So when you having, if you look at the Euler equation, it's a non-linear. So non-linear, the Euler equation behave as hyperbola again. So then hyperbola, these are the technique available for simple problem. So when non-linear time and derivative appear in a hyperbola, definitely you think another technique. That is a time splitting technique. So in the time splitting technique, it's a very useful as well as it's a user friendly, and it has enabled us to calculate a non-linear equations. It's an interesting thing. So in the time splitting technique, there is a two approach, two methods: Lax-van Roof method and Macomart method. These two methods we would use to solve our non-linear hyperbola. This is enable us to calculate only linear hyperbola. So this is the main difference. Okay. So because of the first order wave equation only we will solve here. Okay. So here for Euler equation, when you consider Euler equation set of continuity, momentum, energy, it behave as a non-linear term. So when solve this, I will show you how the non-linearity is present in the set of equation. Okay. Now we'll see each terms in the board. For explicit problems, first one is Euler FTCS. So write your governing equation. So we have the Euler FTCS means generally. So Euler have been give idea for how to solve the wave equation, one dimension form. So that's why the name as Euler. And it's a remaining thing is general u of forward in time. Okay. Del t central in space. This is we have when applied forward in time, central in space. So final objective is I want to calculate n plus 1th value. You can send minus a del t by 2 del x of okay. Now if you look at the quotient value, how can I write it? This is what? C by 2. What's meant by C? This is Corner number. Okay. So this is a general equation. When you apply the domain, we will get how the wave is shifting with respect to time in the domain in the explicit form. So one first method. And second method is Euler FT scheme. Again, second. So forward in time, again ui n plus 1 ui n by del t minus a forward in space again u of I plus 1 u of I n by del x. You can rewrite this form as minus a T by del x. This is again the second method. So if you have a set of bit points, you can apply each bit on this equation. You will get solution for the particular bit system. The third one is Lext method. So in the Lext method, just averaging in the particular location. For example, when you discretize the same equation, applying the forward time central limit space scheme here. After that, at the center node, we have to averaging the values. Again, it forms a minus C, is it? Minus C of 10 to C by 2. So in the U of I plus 1 I power n only, we will give a average values. Okay. So in the average of space plus 1 and the location. So if you have a typical regeneration like this is I minus 1 plus 1 minus 1. So on this I know if I want to calculate the variable by using a Lext method, in that variable I have averaging. For a Lext method, the main difference is, so in the UI term, you have to give a averaging value between I minus 1 and I plus 1. So that has to send in the right answer. So this is a general equation to calculate the variable of the domain by using a Lext method. Okay. Then midpoint leapfrog method. So here, both time and space discretize in a forward difference. Sorry, central difference. Central in time, central in space. Okay. CTCS scheme. Generation. central in space I plus 1 u of I minus 1 by with respect to t with because you can consider n. So with respect to I, the central difference is n plus 1 and n minus 1. By 2 delta. And with respect to x, okay. So after applying CDCS scheme here, we will get here. And the important notable thing is how to get a n minus 1 only. So already you know from parabolic, so there is a startup solution. So we have to mention n and n minus 1 here to solve our problem. There is a drawback as well as it's a stable compared than other methods, are stable. It gives a large number of, finite number of values. So you write u of I plus 1 is our objective. Again, the 2 to get cancelled, the c of minus c only. Okay, alpha del t by del x is a core number. So this is notable thing. You have to give a startup value like 10th level. Okay. So this is a notable thing. Then, so I said when writing upwind differencing scheme, it's an interesting scheme. Why? Because this is a more physical intuition when handling our physical of the problem. So if you look at this kind of situation, upwind so upwinding means the name telling us you should consider your value or node ahead of your reference. Okay. For example, this is a typical grid. Okay, now one dimension. I minus 1, I plus 1. Okay. If the flow takes place or disturbance is coming from left to right. Okay. So you should consider this node for discretizing a space difference. Okay. So how can I discretize? So again you have to use a forward time plus forward space or rearward space with respect to flow direction. So you use which direction is this? For example, left to right. So I should use here backward point. Okay. Now when I discretize it, in plus 1 u of in and del t and discretize it, I should consider u of I minus 1 ui. So when you write a space derivative, discretize a space derivative, so disturbance propagates from which direction? So that direction you have to consider as a preference. Yeah, so this is a upwinding. So upward to our expecting point. Okay. So when you write this equation, again it's a column number. So the same upward differencing scheme I can write when disturbance is this I plus 1, this I minus 1. Okay. So the flow direction or disturbance direction coming from here, how can I discretize it? U of I n plus 1 U of I n divided by del t minus a. So this is U of I plus 1 minus ui by del x. Now what's the differencing scheme is this? What's the differencing scheme is this? When discretized like this, when your flow takes place on right hand side or disturbance takes place right hand side, forward difference, act as forward difference. Okay, so this is a logic. Minus 3 U of I plus 1 minus U of I everything C. Okay. So it's a very important upwind differencing scheme, always hyperbola problem working with upwind differencing scheme. So because of the strongly function of disturbance, you have seen in an earlier lecture I have delivered about how physical meaning is acting regarding to our hyperbolic equation. So this is an arrow. Hyperbolic propagates a zone of dependence, zone of influence. So it's working under a shaded region. So you should consider where is the disturbance from, where is the disturbance takes place. So with respect to the disturbance and propagation, you have to match your solution. Okay, that's why maximum, so many of hyperbolic problem, we would choose and prefer upwind differencing scheme because of this. So which direction is disturbance propagated, that is a preferable, and common sense also telling us it's a good guess. Okay, you consider this where the disturbance node, it's a good guess. Like when you doing your elliptic equation, so 100 degree centigrade, 0 degree centigrade, in between you have to guess the temperature. What's a preferable guessing value, the temperature intermediate node? It's within 0 to 100. So 100 node neighbor guess is, it may, what's a general guess? 30 or 40. When time is keep going on, or space is keep going on, it's a interpolate the value and finally reach a steady state. So like that you have to guess the which direction of disturbance takes place. You can choose that node as a your preference node. Okay. So this is the general technique behind the upwind difference scheme. And so many of technique again, the scientists developed so many of upwind scheme from origin of this equation. Okay, in the later on classes we will see how many differencing schemes and how they updated to efficient our solution. Okay. So up to this we have finished the explicit forms. Is it? So 5 methods available, I think. So now going to implicit. So what are the implicit solution?
Crank-Nicolson.
So first Crank-Nicolson average, you know what's mean by Crank-Nicolson? What should I do on the right hand side? So implicit names as the right hand side also you have to give unknown discretization. So this is implicit. If it is explicit, I should use a nth level. If it is implicit, space matching should be n plus 1 level. And now I want to apply Crank-Nicolson here. What's the general procedure? I should use ui plus 1 n plus 1 plus ui plus 1 n, averaging the value. Remember, and again at the location of ui minus 1 you have to averaging the n plus 1 and n. Okay, so this is a basic idea. 2 del x plus 1. So how can we simplify this? So again del t by del x is minus CR. C by 2 plus 2 del x C by 2 into 1 by 2 0 5 plus 1 plus 1 finished ah? Point only now. So when if you simplify this equation, so from the final equation we have to get n plus 1, all the n plus 1 on the left hand side, nth level is right hand side. Here and this one. So it should be plus c by 4 c by 4 u of 5 plus 1 n plus 1 and so minus plus and minus c by 4 u of 5 minus 1 n plus 1. Okay. U of 5 n minus c by 2. Directly you can write c by 4. Again I can write as 1 by 2 as a common. U of 5 plus 1 nth level minus half.
Plus minus common.
Oh, I have taken minus also. Minus u and minus 1 nth level. Okay. So this is when you apply implicit scheme in a hyperbolic equation, I mean one dimensional wave equation, we will get implicit form as like this equation. And another technique is Euler technique. Is it? So Euler technique is nothing but directly you can write it. Up to here it's Euler technique. No need to averaging them. So like in parabola Lasanan method, can you remember Lasanan method? In the Lasanan method directly you can write n plus 1 level. Like that you have to apply here in hyperbolic. Euler implicit by x n plus 1 So instead of I have used here order difference. That's all. In the space mass I apply forward difference. Okay. It should not present. Next step you have to send it. Plus This also must be. Yeah. Oh, okay, minus. Equal to 4. Okay. This is the other equation. And final method is next one. Like that you have to listen in a direct upwind difference discrimination. Again you have to apply in the right hand side alone averaging. I mean not averaging, say L plus 1 level you have to substitute here when you are handling a upwind difference. This is a dou u by dou t minus dou u by dou s. This is upwind. Okay. First upwind. It should be in a for example flow is I have right psi and I plus 1 psi minus 1. Flow is present in this direction. I have to mark I plus 1 I. So both are in. Okay. This time I have applied the same logic here. Instead of nth level, n plus 1. N plus 1. That's all. Now again gather all the n plus 1 and n minus 1. Okay. So minus c. What should be plus? Upwind implicit. So again when you have a flow direction in this side, what should happen? So in the discretization process, it's a I minus 1 n plus 1 minus of I n plus 1. Okay. So I have considered flow direction in the right to left. That's why I applied a forward differencing here at level of n plus 1. When you are handling in the left hand side, again n I minus 1 minus I. Both are n plus 1 level. So with the nth level, it's again act as a upwind in explicit. Okay, it's a difference. Note down. In explicit implicit method. So in the explicit method, hyperbolic problem, one-dimensional wave equation, what's the stability condition? So C value should be less than 1. This is a stability we have seen in earlier lectures. So it should be below 1. Okay, it should be below 1, then only we will get a smooth solution. Such a methods only for linear equations. So we have seen implicit, explicit, so many techniques. In the 5 and 3, 8 technique we have seen total. So these are the smoothly working under only if you have only linear equation. For example, what about non-linear equation? So non-linear equations, when you consider this set of non-linear equation, This is what type of equation? Continuity equation. Okay, continuity. The next momentum. Listen. Y momentum.